we continue, and especially for our new listeners, I would remind several principal steps of the last lecture. We started to use, for integrability reasons, such a structure which is called the R-matrix Poisson bracket. R-matrix Poisson bracket. So at this moment, I propose to consider it just formally. It's some formula which is useful to demonstrate the integrability. But so it has deep relations with such geometrical and algebraical branches of modern mathematical physics as Lie-Poisson groups, and its quantum version, which is called the quantum group. Quantum groups, which is an algebraic background in the modern quantum theory of integrable systems. So there are very interesting and deep geometrical and algebraic relations with such structures. But we started with a very simple example. We introduced the Lux operator, the JLN Lux operator, which is the sum of matrix units just multiplied by generators of the Lie algebra JLN. And EIJ are just matrix units. I will denote it like this. So these are matrices, and these are generators of the Lie algebra JLN. But we identify the space with the dual space to the dual space of JLN. So we consider them as linear functions on this dual space. Is it clear, or it demands some comments, illustration? So we worked with this object since the beginning of September. Is it nearly clear? Okay. So it means that these objects are linear functions on the dual space. So so we consider EIJ as some functions, but on the dual space. And this ring of functions is a Poisson algebra. So there is Poisson structure on this ring of functions, and it is defined by the Lie-Poisson structure, which is just the commutator in the Lie algebra, which is EIL delta GK minus EKJ delta EL. And then we expand this Poisson structure to the whole field of function on dual space by the Leibniz rule. So now the R-matrix formula is the following aggregate. So we define new tensor notations for the Poisson bracket, and in fact it is equal to PL2 in this case. This is an object. This is an object in the tensor square of the space of matrices, and by n multiplied by our field of functions, fun. And this matrix element is defined IJKL. This is a double index from the first and the second copy of this metric space. It is just Lij, LKL, so it's a function on our phase space in our Poisson algebra. And this formula, formula 1, very important. So it expresses all Poisson brackets of all matrix element of our Lax operator for the J-Line Lie algebra. In terms of some algebraic operations on the space of matrices, not in terms of the Poisson structure, but in terms just of commutators of matrices. And here P is the matrix. Okay, it is equal Eij, Eji, which is the matrix, an element in this tensor square. And it is a matrix. It is a matrix of a linear operator here, which acts by permutations on such decomposable tensors, like this. I suppose that it's not obvious for you. Please make signs, so we'll discuss such the properties of this object during the exercise part. I strictly recommend to write down all these formulas, because we will have many formulas. There is a structure behind, but it better enters our brain if we make writings. Okay, this was this was the introduction for this important formula, and we demonstrated the efficiency of such a representation by the following expression. So lemma. I will just remind the statement because the proof was given, but it is useful to keep in mind, to have in mind. Okay, we introduced such functions in our algebra, which are spectral invariants of this Lax operator. So these are just functions on the dual space to the Lie algebra J-Ln. So the lemma was that they are central. Eij is equal 0 for all k, I, and j. So it means that Ek are element of the center of our Poisson algebra. And the simple demonstration of this fact was given using this formula. So this structure helps to study the properties like integrability. So the description of the center, the description of involutive commutative families is the principal part of the algebraic theory of integrable systems. So this type of formulas is a very helpful tool to demonstrate integrability in many different contexts. So this was the lemma, and this lemma is a motivation of formulas like this. So if in the system which you study we succeeded to find such a representation, we demonstrate many useful and important properties related to integrability. And today we will study the similar structure in the case of the open Toda chain, our main hero for next several lectures. And I will recall its definition, and we will discuss structures very similar to this. Open Toda chain. So we defined it just by the Hamiltonian on the canonical Poisson space. So it is represented by the kinetic term pi plus the sum e from 1 to n, e from 1 to n minus 1, e qi minus qi plus 1. And if we consider the canonical Poisson brackets in the space, this produces the equation of motion, which is q dot qi dot is pi, and pi dot is minus I qi minus qi plus 1 plus qi minus 1 minus qi, if I remember well. I have doubts about the sign, but it seems to be okay. So just in terms of coordinates, we have the equation of motion like this. Minus qi minus eqi minus qi plus 1. And it represents some chain of particles on a line interacting through this exponential отталкивающий. Не помните, как будет отталкивающий. So then such an exponential potential. And so it was introduced for some goals in solid physics, but it turned out to be integrable. And to understand this, we introduced new coordinates, Flaschka coordinates, AI minus 1 over 2 pi, bi over 2 qi minus qi plus 1. And so it's another set of variables for the system, which is useful in several senses. And the Poisson bracket in these coordinates is like this. So all variables A commute with itself, Poisson commute. The same is true for B coordinates, but the mutual Poisson bracket is not trivial. AI bi is equal minus 1 over 4 bi. and a I b I minus 1. bi minus 1 is plus 1 over 4 bi minus 1. Okay, so we considered Lux operator. So you see, by the same letter, we denote Lux operator in different contexts, but we will comment each time. We will comment what is the Lux operator. It is due to Lux who introduced this notation, and so it's a homage of Lux. Okay, in this case, one introduces the Lux operator, which is a three diagonal symmetric matrix n b1 bn minus 1 bn minus 1. And during some previous lecture, we demonstrated the following statement, that this equation of motion for the Toda chain expressed in terms of the Flaschka coordinates are equivalent to the following lemma 1. Equations 1 are equivalent to the following matrix equation M of L, there M of L is L plus minus L minus, which are the projections of the Lux operator to the upper and lower triangular parts. Projections to the upper and lower triangular parts. And this statement was important corollary for the statement that K, which are always spectral invariants of the matrix L, are integrals of motion. And it is the first step to demonstrate integrability. But if you remember the Liouville theorem, it claims that the system is integrable in quadratures if there is a big family of integrals of motion which are in involution with respect to the Poisson bracket. So in each situation, when you represented the dynamical system in term as a Lux equation, you have this corollary. So it's a simple consequence of this representation. It's very simple. So you see, the dynamics in terms of the Lux operator is by the joint action of the Lie algebra. There is some Lie algebra element which just conjugate your Lux operator. So if you integrate it, you obtain an action of the Lie group, a joint action of the Lie group.
What, integrate Lux operator?
Integrate Lux equation.
Oh, okay.
You see, it's an equation which says that your dynamics is described by some adjoint action of the Lie algebra on the Lux operator. The vector field in terms of this adjoint action could be expressed quite in a complicated manner, but it is the form of this action is just the adjoint action of the Lie algebra. If you integrate it, you obtain an adjoint action of the Lie group. we checked by conjugation. And this implies that the spectral invariants are integrals of motion. So this statement is very simple, but I have demonstrated it in just in algebraic strong way. But the Lax representation is not sufficient for the involutivity of this family. So it is not related with the involutivity. It says just that these are integrals. The involutivity is the consequence of some other structures. And this will be the R-matrix Poisson bracket in our case. Okay? So we just repeated the motivation, and now we proceed to the explanation of the integrability of the open Toda chain, and we will use the R-matrix technique. So our aim for today is to describe and to demonstrate the R-matrix Poisson structure for the open Toda chain, and to prove the theorem that if our Poisson structure is R-matrix, linear R-matrix, then the isospectral integrals are in evolution. So let me maybe formulate the main theorem for today. I will formulate in here. So I will introduce an R-matrix, which is the following aggregate. So it's the sum Eij, Eji, but they will be how to say, the delta function. I need the sign of I minus j. Yes. Oh, perfect. E minus if I is bigger than j. Like this. Eij. For in j, and sign will be such a function. So it is equal 1 if I is greater than 0, 0 if I is 0, and minus 1 if I is less than 0. Okay? I need to present you the formula in the simplest example. So if n equal 2, it means that R is E21, E12 minus E12, E21. Do you agree? And I'd like also to present you the form, the matrix representation is equal E12, E2. I'm sorry, E2 if I is greater than J. I is greater. So let us verify this. It's okay, or the sign is wrong.
So the most common question, how do you get the formula for this R-matrix?
It will be the question of the next lecture. Firstly, we will work out this notation and the formula. Is it correct? So you see, there is only one pair of indices. The pair of coinciding indices, it produces 0, so we don't consider it. So we consider Ij, 1, 2, and 2, 1. and for 2, 1, the sign is positive. If for 1, 2, it is negative. So it's okay. When, as you remember, we represent the matrices in the square product of matrices as the bigger matrices. So as matrices 4 by 4. And here is the block 1, 1 with respect to this to the first component in this tensor product. Okay, and here we have the matrix 2 by 2, which is represented by the second element. So this matrix has 0 when we fix the block 1, 1, because we have no matrix element 1, 1 at the first place. In the second place. So we have the block 1, 2, which is this block. And in this block, we have one element 2, 1. So this is the element, this element. And this element corresponds to -1 here. Okay. So this is a representation of such an R matrix. What should we verify? Please verify, but it will be an exercise for our exercise part. Exercise 1. R satisfies the classical Yang-Baxter equation, which is R12, R13 plus R12, R23 plus R13, R23 equals 0. Okay, but for now, the statement will be the following: that this tensor Poisson bracket of our Lux operator for our Lux operator of the open Toda chain is equal, I think it's 1 over 2 R L1 plus L2. So it will be the theorem. But do we understand well what is written here?
What is this?
Yes.
It just R comma L1 plus L2. Okay.
Sorry?
No, that's okay.
It's for general case, for SLN case, but what is written here? What is L1, L2? What is on the left?
The definition in the last.
Yes. So, yes. So this is the element by n square multiplied by our field of functions, which is the R of GLN star, the dual space to the Lie algebra GLN. And here we have the element of the same space. So it is some equality in this space. So it represents the Poisson brackets of matrix elements of the matrix L in the space in terms of matrix element of this big matrix. Okay, this will be our first technical statement, and the next theorem will be the theorem 1, theorem 2, that EK commute this will be proved with the help of such a relation. Okay. Let's start to calculate the Poisson bracket. So L first of all, I will introduce the notation for the lax operator. It is the sum of EII multiplied by AI plus the sum of EI plus 1 I plus 1 I multiplied by BI. 1 to n minus 1 E from 1 to n. Okay?
So A or B are this from the flow property?
Yes. So I just remark that B is multiplied by this upper triangular element and this lower triangular element. There is such a sum. So it is a Jacobi matrix with only 3 diagonals, so it is quite free. Okay, so and this Poisson bracket, or even I will use such notation. So it is the sum of sum of EII AI plus sum EII plus 1 plus EI plus 1I BI sum EJJ IJ plus sum BJ when we can see that the Poisson bracket of A with A is trivial, of B with B also is trivial, and the only thing is the Poisson brackets of A with B and B with A. I will try to calculate it well. So it's the sum of I and J, EII, this EII multiplied by EJJ plus 1, EJ plus 1J, and here FAI BJ. And then this Poisson brackets plus the sum over I and J, EII plus 1, EI plus 1I, EJJ, the Poisson bracket BI AJ, IAJ, and then we use the Poisson brackets in terms of Flaschka coordinates. I will write these formulas as follows: AI BJ is equal to delta minus delta IJ plus delta I J plus 1 yes, J plus 1 J BJ over 4. Do you agree?
Shouldn't the delta be I plus 1j? The second delta?
This one? Let's verify. So this term is non-trivial if I is equal to j.
No, that's trivial, but
Uh-huh.
the other term?
In this case, I is equal to j plus 1. So j is equal I minus 1.
Yeah, but then bj, that j should be
Yes, I minus 1.
I minus 1.
Yeah.
Okay. Yeah, it's okay.
So in this case is bi, but if this index is I minus 1, the Poisson bracket is I minus 1. Okay, very good. And this is equal, okay, I will just repeat it. So it is equal to the sum ij I j, yes. Okay, plus with inverse because it's in inverse order, and I should exchange the indices here. So after all this transformation, it is delta ij plus delta j I plus 1 and bi. Okay, now I will use these delta functions. So in the first step I subtract the index j, but I will fix it to be equal I minus 1. So j is here I minus 1 over the sum over a I. J is equal I minus 1. E I minus 1 I plus I minus 1 b I minus 1. Next term, j is equal to I with the sign minus. I j equal I. I plus 1 I plus I plus 1 bi. Next, here j is equal I minus or I I plus 1 I plus 1 I j is equal I, there is another minus, so it is plus, and bi, and minus the sum over I, and here j is equal I plus 1. J is equal I plus 1.
So we just get rid of j completely.
So let us look at this expression. It is a little bit big, but it is treatable. So we can decipher the structure of this matrix. So there are only elements where one of the matrix element is diagonal, and the other is upper or lower triangle, but of the sub-principal diagonal. You see, in all monomials are of the form e I I plus 1, or e I minus 1, or e I minus 1 I. No. Yes. E I minus 1. Yes. Or just transposed. It corresponds to the fact that the Poisson brackets are non-trivial only between diagonal part of the Lax operator and the elements of the first sub-diagonals. All other Poisson brackets are trivial. Okay? So it just represents the formula which we know, this Poisson bracket in Flaschka coordinates. Okay, let us try to calculate the right side of this of the formula in our theorem. Okay, so let me remind you the R matrix, which is the sign of I minus j j I.
So what do you want to do now?
To calculate the right hand side. So I have to compare the left hand side, which we calculated, with the right hand side, to demonstrate that it's okay. It's the same, and this is the formula for the Lax operator. I'd like to introduce to its part. So you remember it contains the positive and negative part. R plus minus R minus, and R plus is the sum is the sum of Ej, Eij. Here Ij, Ji. So here the positive is the right.
The opposite combination.
So I need that I is greater than j. So, and it means that this part is in this big, is this one. It means that it considers blocks with j less than I. And the blocks correspond to the structure, to the, how to say, the big structure, the upper structure of this matrix. And R minus is the sum of I less than j. What else? They are related by the transposition, obviously, and also by the conjugation of the matrix P. So R minus is the transposition of R plus. Transposition. Transpose. And there is another relation that R minus is P R plus P. There P is the transposition matrix, remember. P is the sum over all elements. It is the matrix which make the transposition in the tensor product of two vector spaces, so it exchanges two vectors. Is this property okay? Is this property okay for you?
Okay.
Just a moment. So the transposition, when you make the transposition of the tensor product of two matrices, it is the same as to consider them both transposed. B transposed. So to transpose this matrix, you make the global transposition. You exchange the blocks. You exchange the ij blocks with the ji blocks. But inside each block, you also make the transposition. Okay? That's why we have to transpose both. Okay. If we transpose R plus, R plus transpose is the sum over I less than j e j I transpose e I j transpose. It is the sum I greater than j e I j e j I okay. And it means that it is the sum over I less than j of e j I e I j if we exchange indices. So I proved this, and for the conjugation with respect to the transposition operator, there is also a P for the decomposable matrix in the tensor square of matrices. It is equal BA. So this is better you verify yourself. So in fact,
I think we have seen this last time.
yes. We used this property many times. And for the matrix of such type, the change of elements on the first and the second place produces exactly this matrix. Because if I is greater than j, then j is less than I. So if we exchange this element, we produce this matrix. So this part of our matrix are related by both transposition and this algebraic procedure of conjugation by the. But it is another transposition. It's not the same operation. This is a transposition in each component, and this is another transposition. Permutation, exactly. Okay, so I'd like to calculate part by part this expression, and firstly with the R plus matrix. all necessary formulas. So I will collect them here. EII, AI, EII plus 1 plus EI plus 1 E BI. This one AI BJ minus delta IJ BJ over 4. Okay, so we start to calculate the R plus L1 plus L2. What is L1? The sum of EII AI plus the sum of EII plus 1 BI, and this is by EKK, also the sum of over K. This is L1, okay, and plus the same, but the exchanged roles of the first and the second component. EII AI and we have to calculate the commutator. Just we'll calculate the commutator. Except that this element 1, it commute with. So when we calculate the commutator, this 1 commute with this part. So we have just to calculate the commutator of these elements. Let me write it. So it is equal to of EJI. Here the sum of this element with this. T plus the sum just T plus 1 T the sum like this commutator, and then we multiply it by EIJ. Please.
I was saying, like in the definition of L1 and L2, there was 1. So
yeah.
didn't write it.
This is 1. Yes, this is 1. The sum of diagonal matrix element, it is the element 1 in matrices. So this element commute with all matrices. So when we consider the commutator of tensor products, the non-trivial part comes only from the commutator of this with this, and this with, and this with this. So it's the first part, and the second, and plus the sum greater than J, I, J, I, commutator ij with this sum. Plus 1 t t b t. Yes, yes.
So the index of E is k only, or what?
The index of what?
Index of E in the first line, in second line.
Here.
Here in the down, yes, index of E. In the definition of L1, index of E is k or m or what? I mean, here in the beginning of third line.
Here.
Yes, yes, yes.
It is not important. It is the sum of independent index k. It is the element 1. We even do not make attention to this index. Because when we commute, so it commutes with this part. So what is written? That A, B commutator with C1. What is the commutator of this element? Evidently, we have to write A, B multiplied by C1 minus C1 multiplied by A, B. But when we multiply, we multiply it component-wise. Okay, so we multiply A by C and B by 1. A, C, B, 1 minus C, A, 1B. But 1 multiplied by B is always B, so it is equal to the commutator A, C with B. And I used this there. Next step. Next step, we know how to calculate, but I'm sorry, they should be ETT. It's better. What is it? So there is a commutator A greater than J. There is a sum over yes, and there is a sum over T. And this commutator is equal A E J I multiplied by A I minus AJ. The commutator of such elements.
These?
Yes.
And the other parts?
I can write it. I can write it.
And other parts will be 0 or
So I calculate the commutator of EJI with the sum over T of ETT AAT. It is the sum over T. And then I commute these elements using the standard formula. So it is EJI delta TI multiplied by AT minus delta from the other side JT and AT. Okay. There are only two terms in this summation, non-trivial terms, then T is equal I and T is equal J. Ji, if T is equal I, when we multiply it by ai, and if t is equal j, we multiply it by aj. Next term. Next term. Okay, but I multiply it by eij. Next term. It is also the sum over I greater than j, and there is also the summation over t. I will write it. I will write it just directly with delta function for at the moment. So when we calculate this, we get e j t plus 1 delta I t minus e ti ti delta t plus 1 j. Okay, and here plus e j t delta jt delta I t plus 1 and minus e t plus 1 I t plus 1 I delta t plus 1 I delta tj multiplied by bt and tensor multiplied by eij. And it is only the first part of this expression, but we are brave. We will simplify it. Okay, I will rewrite it. Just here. So it's the sum over I greater than j. In this part we have t equal I, so it is e j I plus 1 multiplied by bi, t is equal I. Then here t is equal j minus 1. T is equal j minus 1. It means that we have e j minus 1 I, and t is equal j minus 1. T is equal j minus 1. That's why we have here b j minus 1. Then here we have t is equal I minus 1 plus e j I minus 1 b I minus 1, and the last term t is equal j plus 1 I b j. Okay, and multiplied by eij. Please verify this, because I can make mistakes as a human being. So now I ask you to verify just that this part coincides with this part. I specialized the indices in virtue of Kronecker delta functions. Do you think it is principally okay? And we have the next part. So we calculated only this one, if I remember well. Only this one. We calculated only this one. But we have always this one, this J plus. So it is this one. With okay, yes. Okay, very good. And now we have the similar expression plus the sum over Ji. It is the same expression, but we have to exchange I and J. So this expression is the same, but here we calculate the commutator with Eij in place of Eji here. So we have to use the same expression, but with the exchanged indices I and J. And the first part is very pleasant. This commutator. So it will be Eji multiplied by Eij. And the values Aj minus Ai, because we have to change indices I and J. Okay, so this is the first part of this commutator multiplied by Eji. And next we have to calculate this little bit more complicated part, but it is the same as this one with the exchange of indices. So it is the sum over I greater than J Eji I J plus 1 Bj minus I minus 1 J B I minus 1 plus I J minus 1 B J minus 1 minus I plus 1 J B I. Okay. So the pleasant thing that these terms compensate each other. So they are the same, but with different coefficients. And now we have to look carefully to these expressions and to see that they resemble a lot. But we have to change indices in some steps. For example, let us consider this term in the first part of the expression and this term in the second part of the expression. If we change indices here, if we denote the index I minus 1 by I prime, or even better by I.
But we already have I, so it might.
Yes, they will coincide.
But we don't know yet that they will coincide.
Let's see if I minus 1 is I.
Okay.
If you just
yes.
denote this index by I, then they coincide, because it will be j, I'm sorry, ji, yes, ji plus 1, because now I minus 1 is I, so I is I plus 1.
Okay.
Okay. So if we change, okay, I will take it by I prime.
Yes.
So this will be I prime plus 1.
Yes, yes, yes.
They will coincide, but the signs are different. The only the only difference that the summations are different. You see, this summation is very important here. So I is greater than j. If you change the index, the summation will be different. But it's the only one term in each summation which survive after this cancellation. Let us consider it in more details. Just this part, just this part of this formula. We have the summation of I greater than j, e j I plus 1 I plus 1 multiplied by e ij and multiplied by bi. And this summation minus summation of I greater than j, e I minus 1 j, I'm sorry, e j I by e I minus 1 j multiplied by b I minus 1. You see? Let me work out a little bit this expression. I will sum over j, and then I will sum over I greater than j. Sum greater than j. Here I just rewrite the same expression, bi, and here I introduce a new variable. I introduce a variable I prime, which is I prime, which is I minus 1, is not evidently, okay, which is the sum over I prime greater or equal to j. J, I is I prime plus 1, E I prime, j, B I prime. Let us compare the expression. Over j, and then I sum over I prime greater or equal to j. Okay? This change of indices gives this change of the domain of summation. And this difference is just one part of this summation. The only part then j prime is equal, I prime is equal to j. So it's the sum over j with minus sum over j, and we have to take I prime equal to j. J plus 1 E jj I prime equal to j, bj.
It's from here, right?
Yes. These two terms produce only element like this. So now I claim that all other terms cancel in a similar manner. So we will get only the terms like in this formula. So you see only terms with the diagonal term in one component and the element of upper or lower but sub principal diagonals of our matrix. So I propose to finish this calculation during the exercise part.
Finish this calculation means like show how it goes to that one.
Yes, to show all other terms. For this reason, I ask you to make a copy of this calculation. Now I like to prove, however, the principal theorem, how we use this formula, how this Poisson bracket allows to prove involutivity. So our theorem now is that EK, EM commute, and we will use our formula, which is R L1 plus L2. First of all, we need to calculate the following Poisson bracket. So you see, this formula is adapted to matrix calculation of this type. So I even could not could provide you historical details how it appeared. But maybe the most magic part in this story, that firstly people understood the quantum integrability, and then considering it classical limit, they obtained it, the people from the Leningrad school, Fadeev, Drinfeld, Sklyanin, they understood that there is this Ludwig Fadeev. Okay, we will try to calculate the Poisson bracket between powers of our Lax operator, and it is done by the Leibniz rule. I will write you the formula. So in each product we should choose a component between which we calculate the Poisson bracket. For example, we take the eth and jth component in each product, and the other part we took on the left and on the right. So 1 E minus 1, L2 G minus 1. Then we consider the Poisson bracket between eth and jth parts in these products. Okay. And then they take the rest to the right. 1 K minus I and L2 M minus J. Is it okay? So maybe firstly we have to understand the following formula: A, B, C is equal A, C, B1 minus A1, plus, sorry, BC. For the matrix, for the matrices of generic type. So let us verify it also as the exercise during the exercise part. Okay. And then we use our formula, this formula. So here it's a sum. I from 1 to k, I from 1 to k, yes. and J yes from J to one from 1 to m. So it is equal sum 1 to k m J from 1 to m L1 I minus 1 L2 J minus 1 here R L1 R L1 minus L1 R L1 k minus I L2 m minus j. This is the only first commutator here, and plus sum from 1 to k j from 1 to m L1 I minus 1 L2 j minus 1 R L2 minus L2 R L1 k minus I L2 m minus j. Let me rewrite it. There are always such trick as cancellation of such some summations in the R-matrix calculus, but let us do it. To kj from 1 to m L1 I minus 1 L2 j minus 1 R L1 k minus I plus 1 L2 m minus j and minus the summation. I and j are always in the same domains. I, because this L1 multiplied by this power of L1, L2 j minus 1 R L1 k minus I L2 m minus j plus summation with the L2 operator L1 e minus 1 L2 j minus 1 or L1 k minus I L2 m minus j plus 1. So this element commutes with L1. They in different tensor components they commute. So we can transmit it to this power and add this index in the power minus ij L1 I minus 1 L2 j minus 1 but now this L2 goes to this power, so it is j R L1 k minus 1 L2 m minus I m minus j. Okay, here we see that these summations are very similar, so there are similar terms in these summations.
So they will cancel maybe?
Yes, we will cancel each other, but not completely. So how to manage this? So there is a difference of indices in I. So if we introduce here an index I prime, So I'd like that I will be I prime minus 1. I prime minus 1. Then here will be k minus I prime plus 1. Okay? Here. But the summation here, j is always from 1 to m, but I prime is from 2 to k plus 1. Do you agree?
So our I prime is k minus.
I is from 1 to k. It's the place of L1, which we Poisson commute with something. But now we consider new index I prime, which is I plus 1. And this index I prime, it goes from 2 to k plus 1. Do you agree? But if now we make the inverse, so I prime is the index, we can denote it by I. So this summation are different by the domain of index I. In this sum, it is I from 1 to k, and this sum, it is I from 2 to k plus 1. The difference is the value of this for the k equal 1 minus the same index for the index value of this index k plus 1. Let me write it down. So here I should take I equal 1, and it will be the summation to m I equal 1. So it is 2L2 j minus 1 R. And here it is L1 I equal 1. So it is L1k L2 m minus j. And minus the following. Here we should take I prime equal k plus 1. Or I equal k plus 1. And it means that it is the sum over j with the same index from 1 to m L1. So we have changed here I by I prime minus 1. Okay. Now I prime goes from 1 to k plus 1. Okay. So, and we have to take here the value of this summation over I prime with the value k plus 1, because there is no such term in the left hand side. So here we have to take I prime equal k plus 1. Okay. And it corresponds to L1 power k, L2 power j minus 1, R, here the 0th power, and j.
If I equal to k plus 1, then why L1 power k only?
Because it is now a prime minus 1. It was our change of variables. Okay. And for the next two summand, we have very similar property. So now it is the index j, which is different in this two part of summation. But if we introduce here the index j prime, which is such that j is equal to j prime minus 1. Okay. We obtain the same thing, and here we get same expression. And the difference give the following thing. For on the left, we get only part with j equal 1. So we have the sum over I L1 I minus 1 with the 0th power of this term L1 k minus I L2 power m minus 1.
Same construction for closure.
Yes, the same. M and minus the same, but with the bigger L2 on the left. Sum over I L2 power m L1 E minus 1 R E1 K minus I, and that's all. So please look carefully at this expression. And the next step, it was an auxiliary part of our calculation. Now we calculate the Poisson brackets between spectral invariants, and this is the trace over both tensor components of this Poisson bracket. You see? The Poisson bracket is a linear linear function. It commutes with this trace function, which is a linear function on the matrix. Okay, so we have to calculate trace on both components of this expression. So I will trace 1, 2, 1, 2. Yes. Just the cyclic property of the trace. We will use the cyclic property of the trace. So I will. The left-hand side is the following: is the trace of the commutator, L1K. So in the trace over the second component, I can put this L2 to the left. Inside the trace, yes. So, in fact, the trace is a cyclic function. We can multiply it. We can in the trace we can use the cyclic property between the trace. So inside the trace, we can use this cyclic property. So, example, it is equal to R and just M L2 M minus 1 L1 K plus K L2 M L1 K minus 1. Something like this. Okay, this part. And it is obviously 0 because it's a trace of some commutator. I used several times the cyclic property of this trace, but
so the whole construction was for Toda chain.
For the Toda chain.
Yeah, it's complicated, and it seems like compared to Colosor-Moser.
There are similar structures in the Algebraic case. But okay, it was too complicated. In fact, we can guess what is the R-matrix structure using some geometrical properties of this model. We will discuss it in I think just in the next lecture. You will get some important material from the course of differential geometry about the left and right invariant vector fields on the Lie group. It is needed for our consideration. But now we stop for 15 minutes, and after the break we continue calculations during the exercise part.